This is the last module of this course, E540. And in this lecture, we will study about frequency synthesizers. So as the name suggests, these circuits basically they create or produce various frequency. They synthesize frequencies. But we have already studied oscillators, and they also produce frequency. That means periodic output. Say A cos omega t. So then question arises that why we are studying frequency synthesizers, given that we already have circuits which can produce frequencies, that means periodic output. So here, what we find is this omega naught typically will be fixed. And so if we have scenario where we want to change this omega naught, then it will be difficult to use these oscillators. So what we want is a more versatile circuit, frequency synthesizers. And these circuits, what they will do, they will also, of course, produce periodic output. It need not be always sinusoidal, but it could be square also. But here, what we will have is this omega naught can be varied over a range of frequencies. So this is one advantage that we get out of frequency synthesizers. And there is a difference between this frequency synthesizer and oscillator. And the key difference is that this frequency synthesizer does take an external input, but this external input will be another oscillators of very stable frequency. That means the output frequency does not change much with the time. And this frequency typically will be a smaller frequency. And what we will be ultimately producing is the output frequency, which will be a certain factor n times omega r. And this n can be greater than 1 also. So these are the two advantages. There's one more advantage that if we have n is equal to 1, then also the output of this frequency synthesizer is going to be more pure periodic signal. So we will talk about this purity of periodic signal later on, which is characterized by a parameter called phase noise or jitter. So these are the advantages of frequency synthesizers. That is why we go for it. And we will see later on that one of the ways of implementing this frequency synthesizer will invariably involve these oscillators that we have studied. But of course, they will be slightly modified. So one of the building blocks of this is going to be oscillator. There are going to be a few other components as well. So this is the reason why we are interested in frequency synthesizer. Now, there are basically two broad classes or sets of frequency synthesizers. So these are based upon the way these frequency synthesis are carried out. So first is called direct frequency synthesis or synthesizers. in short DFS, or later on we will see that more appropriately direct digital frequency synthesizers. And second technique is called indirect frequency synthesis, which leads to indirect frequency synthesizers. So we are going to study each of these two, and we will talk about indirect frequency synthesizers in more detail. That is going to be the main topic of for this module. But today we will talk about DFS in sufficient detail. So as I pointed out, this is basically direct digital frequency synthesizer. So these have a certain advantage. The biggest advantage is extremely frequency hopping. So here it says that if we have DFS and if it is producing a certain frequency omega 1, and if you want to produce omega 2, then a change from omega 1 and omega 2 can be implemented in very short duration. So this is one of the biggest advantage of this DFS. But there is a disadvantage that these are can be used only for used up to few gigahertz. It's not possible to produce very high frequency. Certainly, it is more difficult to produce tens of gigahertz. So now we will see the architecture of this DFS and see that how it functions. So it has a number of building blocks. So first we have what is called angle or even phase accumulator. And then we have another block, and this is read-only memory lookup table. Then we have digital to analog converter. And then finally we have low pass filter. Low pass filter. So these are the key building blocks of DDFS. And there will be a clock which will basically feed these three blocks, the first three blocks. And it will be, of course, fed by F clock. And there will be another parameter M, fed to the angle accumulator. And this can be used to change the frequency of the output, this FO. So we'll see the relation between FO, F clock, and M. So here, what is the basic idea behind functioning of this is that uh, we know that suppose we want to produce uh, this output as a sine theta, where theta will be omega naught t. So this is the kind of output we want to produce. So we know that to get the value of this output, PO, at any moment of time, we just need to feed this angle theta into this sine function, and then we will have this output voltage, which will be of sinusoidal of frequency omega naught. So what we need to do is we need to feed these angles, and what we can do is we can store all those angles here in this angle accumulator. So we can first decide the how many angles we want to store. That will decide the let us say resolution, and we will see that that will also decide the frequency that we can be produced. So here we know that this theta is going to vary from 0 to 2 pi. This is the range over which it will vary. And for any given angle theta, the sine value will be clearly the projection of this vector on the y-axis. So what we do is that we store very large number of these angles in the angle accumulator. So we can first choose a number of bits that can be used to store the number of these angle informations. So for example, if we take n is equal to say 4, then so if we take 4 bits to store these angle information, then we will be able to store 2 raised power 4 is equal to 16 number of angles. So this 16 values over 0 to 2 pi range will be stored in the angle accumulator. So if we take 8 number of bits to store the angle information, then of course we will be able to store 2 raised power 8 is equal to 256 number of angles. So you can see that now there will be more number of angles. That means you will have more number of these sine values, more number of samples. So on and so forth. So if we take, say, for example, 16 number of bits for storing the angle information, then we will be able to store 65,535 number of angles, and then we will have a higher resolution. So what is done is, in this fashion, one can choose to store a certain number of angles in the angle accumulator. So what this angle accumulator will produce on the output side is that at every clock edge, it will produce one angle information at the output. So this V1 will be something like this. Say it will start from very low value. So what it will do is it will keep on outputting or providing at the output these angle informations starting from 0 to 2 pi, like this. So at every clock edge, one of these angle informations will be produced. So let us say that we have up to here 2 pi. So this completes the one cycle of the sinusoid. So output V1 is going to be like this, and all these will be at every clock edge. So that means the gap between any two angle information, this is going to be equal to T clock. So now once these angle informations are fed up to the lookup table, what lookup table basically stores is the value of these sine functions, of course, for A is equal to 1, and for each of the respective angles. So what this lookup table will produce at its output is basically sine theta. So now what we will see at the output of lookup table is, say, these values. See, this is, for example, here we have 10 samples. So we will get these kinds of output from the lookup table. Like this. So here we can see that we have one cycle of the output sinusoid function. So V2 is going to be like this. Now what we have here is these digital samples. So it has to be ultimately converted into analog. So this digital to analog converter, then it will produce output which will be sinusoidal. So the output of digital to analog converter is going to be like this. Here. So we have this kind of output, and you can see that this is not going to be a very smooth sinusoid. So it has steps. That means high frequency components are present here. So one needs to filter out those high component frequencies. So that is why we have this loop filter. So once this signal is fed to the loop filter, the output, final output is going to be smooth sinusoid. So VO is going to be like this. So this is how this DDFS works. So here we can see that what we have done is that we have taken 2 raised power n number of samples to produce one sinusoid. So its period is T naught, and frequency is F naught. And this T naught was produced by using various number of T clocks or F clock. And how many numbers of T clocks we have used is equal to, in this case, 2 raised power n. So we use this many number of clock cycles to produce one cycle of the output. So here we can see that it is 2 by n, T clock is equal to 1 by T naught. That means F clock by 2 raised power n is equal to f naught. So this is the relation we see. So from here we see that f naught is going to be smaller than f clock. So this is what will happen if we do not have m, or if we take m is equal to 1. So this is the relation we will get. F naught is equal to f clock by 2 raised power n, if we choose to use n number of bits to store the angle information. Now suppose we want to vary this f naught, then what we can do? So what we can do is we can introduce another parameter, and this parameter is m. So what this parameter will do is it will decide that what are the angles that we are reading out of 2 raised power n angle informations which are stored. For example, earlier we were basically reading every consecutive angle information. Say this one, then this one, then this one, so on and so forth. So we read total of 2 raised power n number of angles to create one complete cycle. That means to cover this circle once. Now what one can do is, instead of reading each of the consecutive angle informations, one can, for example, read every alternate like this. So we are skipping these intermediate values. So now if we do this way, then you can see that we will be able to read the complete cycle, or we will be able to cover this one complete cycle in less number of clock cycles of the f clock. So if we say take m is equal to 2, m is equal to 2, then in this case we will be basically traversing 2 raised power n divided by 2 number of samples. So these many samples we will now read, and these many samples will be read in t clock duration. So once we read the complete cycle of the angle, which will take this much time, we will be able to produce one complete cycle of the sinusoid. Right. So now we can rewrite this equation as, because m is 2, so 2 raised power n by m t clock is equal to t naught. So that means m by 2 raised power n 1 by t clock is equal to 1 by t naught. That means m by 2 raised power n f clock is equal to f naught. So here we see that output is now going to be m times f clock by 2 raised power n. So we have kept the clock frequency constant. We have kept the number of bits that we are using to store the angle information. But now by introducing this additional parameter m, we will be able to change the output frequency. So for example, when we take m is equal to 2, so then we see that we will have to f clock by 2 raised power n. So this way we can change the frequency of the output by varying the parameter m. The largest frequency that we can produce. So for this case, we will take m is equal to 2 raised power n minus 1. So we will have to take a minimum of 2 samples so that we can produce this sinusoid in a more legitimate way using the Nyquist criteria. So the f of max that we can have is 2 raised power n minus 1 as was pointed out, the biggest advantage is that as soon as you change the M, the output changes. So it takes very less time to change M and change the final output. Of course, there will be slight delay involved related with these blocks, but these delay are still less compared with the delay involved in indirect frequency synthesis, which we will see in more detail. Now we are going to talk about indirect frequency synthesizers. So the block level architecture of this IDFS is like this. So in the previous architecture or DFS, we saw that it also required one periodic signal in the form of F clock, the clock signal, and the output were always less than the clock frequency. So here also we will be also requiring one F ref. So previous F clock can be also interpreted as F ref. A reference frequency will be required, and this will be like the previous case, periodic signal of fixed frequency. And then this IDFS, it will produce and output FO, say F sine omega naught t. And here the relation between F naught and F ref is going to be like this. And very often n will be greater than 1. So here we can use a small frequency reference source and produce a significantly larger frequency output. So based upon this n, these frequency synthesizers, they are broadly subclassified into two subclasses. First one is called integer n frequency synthesizer. And as the name suggests, here n is integer, of course, positive integer. And from here, you can conclude that the F output will always be greater or equal to F reference. And the relation will always be integral. That means output will be 2 times, 3 times, 4 times, so on and so forth. So of course, if we have a scenario where we want frequency output, which is say, for example, 1.5 times of the F reference, then this cannot be used. So then we have a second set of frequency synthesizers. They are called fractional and frequency synthesizers. So as the name suggests, here n is not going to be an integer. So this can be fraction, but of course greater than 1 also. And in this case, then one can produce output which need not be integral multiple of the F reference. But here also this relation holds true. So we will see that this relation will always be satisfied. And these outputs are a little bit slow compared with integer and so now we are going to see the internal architecture of this IDFS. So the most popular way of implementing this IDFS is PLL based. So that means page log loop based frequency synthesizers. So its architecture, it has a number of blocks. So if you see the internal circuitry, we have basically 4 blocks, excluding the FREF block. So we have this block PD, then LP, then VCO, and divide by N. So output is going to be here. And here you can see that there is a loop. And this loop appears in the name also. And this loop, as the name suggests, basically processes the phase, and it tries to log to the phase. So we'll see in more detail how this functions. So here output is going to be a sinusoid or another periodic waveform with frequency f0, and f0 will be n times of fref. So here you can see that this n appears because of this divider appearing in the architecture of this frequency synthesizers. So it is said that this PD block senses the what is called the phase of the F reference and the phase of the divider signal, and it produces an error proportional to the error between reference phase and the divider phase. And this, as the name suggests, this frequency divider basically takes a periodic signal of frequency f0 and it produces and f divider output equal to f0 by n. Now we will talk about in a little bit more detail what are these building blocks. So first one is PD. This is phase detector. And it is this block which plays the key role in functionality, and it is because of this the name has been given as phase lock loop. Then the second block is LE or LF. Actually, more appropriately, it should be called LF. This is called loop filter. So as the name suggests, it is basically a filter, and it has role in deciding how quickly the output settles. So when the circuit is switched on, there will of course be transient output. That means output frequency will not be equal to f0, and then it will gradually settle to f0. So here you can see that this is a loop, a locked loop. So it basically tries to track something. So fundamentally it tries to match the phase of this reference with the phase of the divider signal, and in the process ensures that the output is f0 with relation f0 is equal to n times fref. So we will see later on that how it functions. VCO is voltage controlled oscillator. So as was pointed out, the building block, one of the key building blocks is going to be oscillator. So we have already studied oscillators, and they produce periodic output, but they are used in this architecture, in this PLL loop, to achieve more ability to tune this output. That means to be able to change the output over a wide range. And not only that, create output which will be of larger frequency compared with available oscillator of fixed frequency. And as the name suggests, there is a voltage which can be used to control the oscillators. That means basically the output of this oscillator. So here you can see that the output of this PLL is fundamentally the output of VCO block. So and this input is going to be voltage, and this will decide this output frequency, this input voltage. And then we have a frequency divider. And it is this divider which allows to obtain the frequency greater than the F reference. You can see that if n is equal to 1, then output and reference frequency both are going to be equal. So here you can see that this is the equation. So PLL ensures this equation. So for n is equal to 1, F naught is F reference. So we have a circuit, we have a loop which functions on phase, which processes. Here you can see that the phase of two signals, reference and divider, and then it ensures that the output frequency has this relation with the reference frequency. So we would now like to see that how this functions, and before that we would like to see that why we are talking about the phase when we want to ensure implementation of an equation in frequency. So these are the frequency equations. So why we are processing phase. So first we would like to see revisit the meaning of phase, and then from there we will try to arrive at these equations. So phase of say sinusoid signal. So we know that these sinusoid are basically projection of phasor. So this is phasor A, and it is rotating with angular velocity omega. And so at any given moment of time, it will have angle, say theta, and at this moment, the sine value is going to be a sine theta. And since this phasor is rotating with angular velocity omega, so this will be a sine theta t. That means this theta will be changing with time. And here, this complete argument is called phase. So the complete argument is called the phase. And we know that this angular velocity omega and the angular displacement or the phase for electrical engineer, and angular displacement for mechanics will be given by this equation. So angular velocity omega is time derivative of the angular displacement or the phase. So frequency, angular frequency is equal to d by dt of phase. So this is the key relation which will allow us to appreciate that why we are processing phase to ensure frequency equality. So now we go back to our loop. Let me once again draw here quickly. So we have this loop, and what is being done here is phase of reference is being fed and the phase of divider is being fed. And this PD is basically producing an error proportional to the error between the phase of reference and phase of the divider. So designation of these signals in terms of phase is for the purpose of understanding this functionality of this loop. But actually all these signals, they are going to be voltage. So for example, here there is going to be say sine theta r, say V1, and here we will have say Vd sine theta d, and then here ultimately there will be a voltage not of sinusoid form, but there will be error voltage that will be proportional to this phase difference between these two signals. But the signals will always be voltages at most of the cases, except somewhere between this PD and LF. And as the name suggests, VCO is of course fed with certain input voltage, and then it produces output voltage of from this type of signal, and which will have frequency omega naught. So everywhere voltages are involved, but for the purpose of formulating, we talk in terms of phase quantities. Okay. So here we have a loop, and as we know, this loop will basically try to make this error zero. Ideally, if loop is successfully logged, it should be equal to zero. But there are three possibilities in general that can happen with this error output. So it could be either zero. This is ideal scenario. This is what we want. Or it could be equal to K, and this is constant independent of time. That means in this case, what we have is the theta d is equal to theta r. The phase of two signals are equal. And in this case, it is not going to be equal. We will have theta r minus theta d is equal to a k. And this is going to be independent of time, while these two are going to be dependent with time. So this is second possibility. Third is that we have theta e, which is dependent upon time, not constant with time. That means varying with time. So these are the three possibilities. Now, if we have these three, then what will be the relation between the output and the input frequency? So here, what we see is theta r minus theta d is equal to theta e, and theta e can have value either 0 or k or time dependent value. So now if we differentiate this, what we get is here. So we see that for case 1 and 2, That means for this case and for this case, the right hand side of this equation is going to be 0 for case 1 and 2. So right hand side will be 0. And what we are going to get on the left hand side, omega r minus omega d. So this is what we are going to get for two cases, and this implies omega r is equal to omega d, but there is a divider which is producing this omega d, and what it is doing is it is dividing the output frequency by factor n here. So what we see is n times omega r is equal to omega naught. So we find that for case 1 and 2, we get what we wanted here. And these two cases implies, or these will be called as locked state of the PLL. We will say that loop is locked. That means this loop is able to track this reference frequency. So this is, and of course, in the case 3, when this error between these two phases is varying with time, so of course it will keep on varying with omega. This is not going to be 0, not equal to 0, so we will not be able to get this for case 3. So now question comes that since we wanted the relation between frequency domains, so why not to set up a loop called frequency locked loop? So let us see that how this loop is going to work. And what will be the output? So we are now studying FLL. So this is going to be similar to what we studied earlier. And divider and then fed by FREF. But only thing is that now we will have here frequency detector. That means FD. And in this case also, all the signals are going to be voltages. But for the understanding how it works, we will designate the quantities as FREF. So it is FREF which is being fed here, and it is FD which is being fed here, and then F error is being produced here. And this will be, of course, the input voltage. This will be output voltage of form A sine theta naught t. So what will be produced here is error equal to F reference minus FD. And this FD is, of course, F naught by N. So here also what this loop will try to do is, or it will try to get locked. That means it will try to make this ideally F error is equal to 0. But here also FE can have any of these three cases. Case 1 equal to 0, case 2 equal to constant, and time varying. So these are the three cases possible here, like the previous case. But here we can see that only for case 1, we will have Fe is equal to 0, and this implies F ref minus Fd is equal to 0. And since Fd is Fo by N, so we will have this equation ultimately saying that Fo will be equal to n times f ref. Here keep in mind that only for case 1. For case 2, where in the previous case we had achieved our desired goal in terms of frequency relation, here it will imply that f ref minus fd is equal to k. So here we see that f ref is going to be fo by n plus k. So here we see that we will not be able to achieve this part of the relation. There will be undesired term in the form of k. And of course, for case 3 also, we will not be able to achieve this equation which we wanted. So here we see that if we try to set up a frequency lock loop, then it is more likely to fail in ensuring uh, the frequency equality which we wanted, this relation. However, when we set up equation for the or circuit for the processing phase, then there is a more flexibility in achieving our desired goal, because the quantity which we are looking for is derivative of the quantity which is being processed. So that is why we use PLL rather than FLL for achieving this frequency equality. Now we are going to talk about the other building blocks. So this is a loop filter. So as the name suggests, this is basically a filter, and this will be typically of low pass nature. So what it does is this PD produces a voltage which changes typically with time, because it is being fed by two signals which will be changing with time. So this theta E will be producing a voltage V, which will be typically varying quite fast with time. So this loop filter, it tries to basically extract the DC part of this. Later on, we will see that why DC part. And then that is fed to VCO, and then VCO finally produces output of desired frequency. And this loop filter has a role in deciding that how fast this output settles to the omega naught, the stable frequency. So the transient duration is quite closely dictated by this loop filter. Then we have a important building block, that is, let us first talk about divider. So as the name suggests, it basically ensures that output of this block is n times of its input, and this input is ultimate the output in which we are interested. And this then finally implies that we are able to get output which is n times of the f ref. So there are various ways of implementing, but typically we go for the digital implementation of this divider block. Then another important building block is sorry, this one is second building block. This is third, and this one is fourth. So this is voltage controlled oscillator. So as the name suggests, the output of the voltage control oscillator, which is going to be a periodic signal. And here we are more interested in frequency rather than the amplitude, because this circuit, PLL or frequency synthesizer, is circuit aimed at producing various output frequencies. So although output is voltage, but we are interested in frequency. So as the name suggests, the input voltage to this VCO will dictate omega naught. What we will have basically is here, this kind of output. So omega naught is function of input voltage. And ideally, we want this kind of relation between input voltage and the output frequency. We will have omega C, and this is called free running frequency or free running output of VCO. That means when Vi is 0, output is a periodic signal of frequency omega C. And we can write relation between the output frequency and the input like this. Here. So here K is constant, and it is called VCO sensitivity factor. So here this K is basically the slope of this line. So we can see that if K is more, then the graph is going to be like this. That means even a slight change in the input voltage will have large change in the output. But here you can see that the change is only small, this much. But now change is more. So the higher K implies that the VCO is more sensitive. A slight change produces large output voltage. So here I have written that omega naught is function of Vi, but strictly speaking, this output is a sine theta. That means the phase and the sine of that phase is going to be the voltage that we will see. And since we know that output frequency and phase, they are related in this way. So the sine function can be, strictly speaking, written in this form, assuming that the initial phase is 0, from 0 to certain t, and this omega naught will be determined by the input voltage. Therefore, the output is going to be like this. And we have already seen what is the equation that omega naught will follow for this VCO given by this equation. So we can rewrite this as, so we have to integrate this part, this whole thing. And since this omega c is constant, so this will simply become omega ct plus k into integral of Vi with time. So it is this expression which will be the argument of the sine function. So omega ct plus k into integral of Vi dt. So it is this output which will be produced by the VCO and also by the PLL, because PLL output is same as the VCO output. Now quickly, how possibly we can have a circuit where we we can change the output by changing the voltage. So we can see one specific implementation. So we have already seen the cross couple oscillator here. So here we saw that this is L, C, L, C, R. So here the oscillation frequency is equal to 1 by square root LC. So if you want to change the oscillation frequency, that means if you want omega naught to be dependent upon certain input voltage, then typically it will be easier to change this total capacitance that we see here. So this can be realized with the help of MOS so that it is easier to fabricate. So we can use the CGS and CGD of MOS to implement variable C, or that means varactor. So what we can now do is we can connect a MOS here, because this capacitor basically appears between drain and VDD. VDD basically means AC ground. It does not change with the time. So we can take another MOS. So we will have here a gate to source capacitor and gate to drain capacitor, the two strongest capacitors. So we can now short these terminals so that these two capacitors they come in parallel, and then we can have a voltage here VI. So actually these two capacitors, gate to source and gate to drain, they are affected by the voltage between gate and drain or source terminal. So if we vary this VI, that means the voltage between gate and source or drain, then these capacitors will vary, and ultimately uh, the total capacitance between drain and ground will also get affected. Similarly, on the other side also, we can have MOS, and this is also connected to same input voltage here. So what we will have now is equivalent scenario consisting of capacitor. So this was our original capacitor, and then we will now have two capacitors in parallel. So this will be now the scenario of one half of the cross couple oscillator. So equivalent scenario is going to be like this. So we now see that total capacitance is C, the original C which was present, CGS plus CGD. We know that these two capacitors, they are dependent upon VI. So now the omega naught is 1 by square root L, C plus CGS plus CGD, and these can be varied with VI. So one can change the oscillation frequency. And these capacitors, they will vary in this way, typically like this. So this is going to be the C maximum that we will obtain. And this VI typically can be varied only up to VDD, because maximum voltage on the other side is VDD. So this much of variation of capacitance we can achieve. So here we can say that this is C variable. Of course, this is not going to be very linear as was desired, but still we will be able to change the oscillation frequency.